Dear all, I hope you are doing good. And on day number one, we have started quantum machine learning. I explained from the basics of quantum, and then we have done some implementation for quantum use case where we have learned how to design circuits and how to apply them with machine learning. Okay, as discussed yesterday, quantum is a smallest unit in physics. Okay, that's what I told. Quantum is a smallest unit in physics, and it possesses energy. We do have particles like electron, proton, neutron, photon, atom, which revolve in their layer, and they do have energy. We call them as energy levels. They possess multiple states, which we are calling as quantum states. And quantum itself means superposition of various states or multiple states, because if we do have 0 or 1, that is already present in other kind of learning. But what is different in quantum is when we take superposition of these states. There are events which may occur comprising of multiple states. Last day, I explained tossing of a coin where we can have a superimposition of head and tail both, or 0 and 1 both. Therefore, according to the quantum theory, presence of 0 is there, presence of 1 is there, and presence of both is there. That's something which is interesting. We are calling it as superimposition. A state where both 0 and 1 are present, represented by alpha 0 plus beta 1. Alpha and beta are probability amplitude. They are the measure which tells how much amount of 0 and how much amount of 1 will be present. Therefore, quantum equation will be like this. Obviously, there is nothing else by the help of which we can describe a quantum equation. One point came into my mind. If I write alpha 0 plus 1 minus alpha 1, what does it makes? Does it makes any kind of sense? Then I thought that we have gone through different quantum gates, and according to the quantum gate and the condition of quantum probability, whether it will be satisfied or not satisfied, that will be a problem. That's a problem, because according to quantum, condition alpha square plus beta square should be equal to 1. They are now representing the probability. Okay, let's say alpha is point 0.8, beta is point 0.6. So alpha square will be 0.64, beta square will be 0.36. It means that 0 is contributing 64% and 1 is contributing 36%. We can do one thing. Don't write this. It's better y equal to alpha square 0 plus 1 minus alpha square 1. This will make a sense according to me if you're talking about a probability, because from here we will get the condition satisfied. This equation will be true. Okay. According to the property of quantum, they also told that one particle will influence another particle because they are connected in a circuit. So obviously they are going to influence each other. This already probability already there, and we can write as alpha 0 beta 1, two states 0 and 1, and we can combine them also mentioned here. That will represent a quantum. Okay. Then I told that this quantum can be associated with machine learning because machine learning have its own y equal to wx plus b, and then we have prediction y dash, then y dash minus y is error. So like we can calculate square error. We can take sum of them, later on average. This will be called as MSE, mean square error. So like the same thing can we do with the quantum. The point is, yes, we can do. We have also studied yesterday, optimization is possible for it. All right, but the optimization we are going to take traditional ML optimizer like Adam, or we can take Nestro. Last day we took Nestro. While designing such systems, I've also told that you have to follow some steps. Initially, you will be having classical bit 0 or 1. You need to convert it into quantum first. After converting into quantum, there will be processing of bits, and this will be processed by a quantum circuit, QC. And after processing, there will be measurement means there will be drop of quantum levels and it will be transformed into classical units, again 0 and 1. Okay, that's what will happen. And after measurement, when we get this 0 and 1, now you can perform the optimization. Okay, and this circuit will again be iterated. Iteration will be performed. All right. This block in presence with machine learning optimization will convert the entire architecture as hybrid. Therefore, it will be called as quantum machine learning. This is hybrid in nature. And why we are applying quantum? Because to solve much more complex problems of a real world, we want quantum processing, which can simultaneously take multiple states. Also explained you that we do have the gates present with us in quantum gates they are. And Hadamard was one of the gate which I focused more. In Hadamard there was a matrix written as 1 by square root to 1 1 minus 1 1, something like that. We do have a matrix in Hadamard gate. Okay, let me just check it out again. Yes, 1 minus 1. This was the matrix. And we apply input, that means 0 or 1 to the Hadamard. It becomes 1 by root 2, 0 state, 1 state, like this. And tells 50-50% chances of appearance of 0 and 1. You've seen last day in the article I already explained. And other question also came, sir, like we do have rotation also, we do have C naught also. Let me share my entire screen. I have prepared some notes related to it. What these gates means, we can have a quick recall or a quick understanding of other gates too in quantum. Let me explain. Here they are. Quantum gates or unitary operators can be classified into several types based on how many qubits they act on and what operation they can perform. How many qubits? 0 and 1 are qubits. If we are taking single qubit, these gates operate on one qubit at a time. One qubit at a time. Either they will work on 0, either they will work on 1. Okay, so for single operations, we are going to take here identity gate, single qubit, one qubit at a time. If we apply these bits over identity gate, there is nothing to get changed because identity is like this: 1 0 0 1. This is identity matrix. So it is identity gate. We do have polygates also, not polyx, not gate. That means not is negation. Okay, not is negation. A input will be negated as A bar, B input will be negated as B bar, or I would say 0 will become 1 or 1 will become 0, like this. So it's a NOT gate. About x-axis it is 0 1 1 0. About y-axis it is 0 minus I 0, that means imaginary. And about z-axis it is 1 0 0 minus 1. So these are polygates, NOT gate. For what I'm talking about, single qubit. Hadamard, this is Hadamard. 1 by root 2, 1 minus 1. We have applied, and it creates superposition. It creates superposition. That's why it is important. So if I need to superimpose 0 and 1, I am going to use Hadamard gate. We did last class. Phase gates also, S gate, T gate, rotation gate. These also I think we have seen rotation matrix. Okay, R x theta, R y theta, R z theta. Okay, so rotation about x axis, rotation about y axis, rotation about z axis. Okay, phase gate, change in the phase or change in the angle. That is what we are going to call as phase gate. 1 0 0 E. to the power I phi. Okay, this is phase gate. So for one qubit, in all these gates, we are going to give one qubit, and they will perform the respective operations. Now, if you want to give two qubits, then the gates are C naught. Yesterday I have used C naught, controlled naught, not like simple NOT, C naught. This will flip the target qubit when control qubit is 1. This will flip the target qubit. And obviously, not means the flipping only. No? Not means flip only 1001. That is not only. Where here they are calling it as a controlled C naught. And the matrix is like this 100 and 0 1 0 0 0 0 1 0 0 1 0. We can apply the C naught when we are considering two qubits. Okay, controlled Z applies Z gate if control bit is 1, controlled Y. We do have a swap gate also, swapping of the bits. We are having control phase gate applying phase shift conditionally. So there are certain gates, and all are, you can see, either trigonometric, either logic based. Okay, and their application is with respect to single qubit or two qubit or three qubit also. Here we do have three qubit also, three qubit gates. CC naught. So naught is single qubit, C naught is double qubit, CC naught is three qubit. Here it is. CC naught. Two control qubits and one target qubit. If both controls are one, target flips. Both are one, target will be zero. Quantum version of the classical AND gate. Okay. This is AND gate. Quantum version of classical AND gate. So if both controls are one, target flips. Okay, target will change. So we have to understand in that perspective only. Other also, there are many gates which are mentioned here. Universal used are HT, C naught, and as a rotation, and all these are used. All right. Their applications, let me tell. Identity, as we have seen, used for circuit alignment and the timing, keeps the qubit unchanged. When we need to perform the alignment in a circuit, and apply identity, because qubit will not change by that. X naught will change the qubit, flip the qubit 1001. That will happen. Y will again flip the bit and flip the phase also. It is used for error correction and state manipulation. Z will change the phase used in phase encoding and quantum error correction. Things are very much in detail. Okay, and it's a separate topic to learn to understand. You are seeing many gates here with the application, like Hadamard create superposition. Okay, essential in every quantum algorithm. S gate apply 90-degree phase, T gate apply 45-degree phase. Phase gate perform encoding of phase. Rx, Ry, R theta, rotation about x axis, y axis, z axis. Okay, this is for 1, this is for 2, and this is for 3. I am mentioned in the table, but things are very much in depth. Things are very much in depth. If you see again our equation, like alpha 0 plus beta 1, presence of these amplitudes, we are calling it as probability amplitude. All the concepts which we have studied so far related to quantum gate, this equation is responsible because because if I talk about Hadamard applied to zero, only one bit. They already told. At least we should remember few things. Only one bit application. Either you apply to zero, either you apply to one. So Hadamard applied to zero. An equation of Hadamard is 1 by root 2, 1 minus 1. To this bit we are applying. And they told result is superimposition of 0 and 1 both. So result is 0 bit, 1 bit divided by root. That's the result they are talking after applying Hadamard gate. So in a circuit, obviously we do have a gate. And logic gates we have already studied in physics. This is also physics. Concept of quantum is physics only. And logic gates also we have studied in physics. But in logic gate, we are taking taking bits only, but not together. There was no superimposition in logic gates. Okay, but here we are having superimposition in quantum. You every well knows about AND gate, OR gate, NOR gate, NAND gate, exclusive OR, exclusive NOR. You have studied all these things in engineering also, I guess, in physics. In your schools also, you studied about this logic of gates. But now, but now we are in an advanced concept of physics in terms of quantum where we are applying superimposition, and these bits will pass through gates only. Bits will pass through gates only, but the question is how many. If one bit is passing, you are called as single qubit. Two bits are passing, two qubit. Three bits are passing, three qubit. And with respect to them, respective gates are used, and every gate is performing some task. If you are a researcher in quantum, then you need to go in depth and learn all these things. For example, two bits, c naught, cz, cy swap, I swap, three cc naught, c swap, multi, that is mcx, multi controlled x, multi controlled z, complex logical operations. And in quantum, we are doing logical operations only. If you see, 0, 1 bits, these are logical operations. That is what we are performing. Okay. But we should stick to some fundamentals, easy only, like this one is good. Rotation also, I have talked about. I think, and C naught also, we have used this much is enough. C naught creates the relationship between the particles. Okay, enable correlation between the feature essential for quantum classification regression. Okay, I am happy till here. Classification regression, because I want to attach this concept with machine learning. So classification regression, all these things will be okay for me. I will do. Okay. Hadamard I can use for superimposition, that will call as a quantum, and if required I can use rotations for quantum neural network. This much I can do. But if you want to go in depth, then there is a list of all the gates. Got it. Another thing, very important. Well, if we want to take a data having images, very important. I consider MNIST digit data set. MNIST is a benchmark data set. It is having two types, like one is digit, one is fashion. Okay. And if you want to start with classification task now, you can take MNIST digit or fashion, and you can apply your models, And once you get the success, then you can switch to other models, advanced models. Okay, advanced models means these model which you have applied over here, you can incorporate some changes or whatsoever you feel you can apply on other data set. But kindly start from here. Start from these data sets. MNIST is having images of dimension 28 to 28. Overall is 784. Now, if I need to encode 784 values, we need 2 to the power n greater than equal to 784. This value should be satisfied. Last day also I was telling 2 to the power n, if you remember. If you do have one feature, then 2 to the power 1. Okay, if I'm having two feature, I will take 2 to the power 1. So there will be 0 and 1. These two qubits we have used yesterday, if you remember. We have already used these two bits. But if like 784 values are present, size of the image is 2020, and if I flatten, convert it into like one dimension, 784 will be the length. This much number of features are present. How many qubits will be required to represent this much features? 2 to the power 9. How much is 2 to the power 9? Is it greater than 784? 2 to the power 1, 2, 2 to the power 2, 4, 2 to the power 3, 8, 4 is 16, 5 is 32, 6 is 64, 7 is 128, 8 is 256, 9 is 512. So 512 is not greater than equal to 784. This condition is failed. 2 to the power 10 is 1024. That means now condition will be satisfied. Therefore, minimum number of qubits required to represent 784 feature image is 10 qubits. So 10 qubit circuit is required. See here what they have written. Expensive to simulate on a classical computer. That's what yesterday I was telling. You are working on local machine CPU. I don't have quantum machine. I'm just simulating. Last day I used Penny Lane library. Today I will use some other library, and I try to simulate a quantum environment. But the point is, creating such kind of circuit is very challenging. So the common approach what we follow is classify only two digits, either between 0 and 1, 3 or 8 or 4 or 9. No need to classify. You cannot classify the entire digits. Okay, classify two digits. Flat. And how to do? Flatten the image, that means convert it into 1D, apply PCA, principal component analysis, dimensionality reduction. I am also not working on all the dimensions. I will apply PCA and I will reduce the dimensions. Let us say reduce to four features only. Last day you have seen the code, we have reduced the features. I can't work on all the features. Total number of features are 764, and I am reducing it to 4 after applying PCA. That means from these images, I am trying to extract the variance which will be explained the highest. That means that means I'm trying to identify as much as information which I can achieve from the existing images, because I need to reduce. I want only important information, not all the features, because circuit cannot be prepared in this way. So four feature encoded into four qubits, and train your classifier. Four qubits, okay, simplest. 10 qubits, difficult. Okay, so four features. Okay, how it can be greater than equal to 2 to the power n? So 2 to the power n, 4 2 to the power 2, so n is equal to 2. We can make required number of qubits will be 2 qubits. I think that's enough for four features also. 2 to the power n. Here is the flow. Here is the flow. MMNIST, PCA, 4 feature, angle encoding, quantum circuit, over. Got it. Just a basic of what we can do. One more thing came into my mind, that can we apply convolution, feature extraction from the image, reduce the features. Then can we apply PCA, further reduce the feature. From here, we will get relevant features. After applying PCA, we will get high variance features only, high information, and then we can apply quantum. This thing came into my mind. I like many of the recent QML papers, such kind of thing is present. All right, fine. So here you can see in my codes, I've already codes, notes, I've already shared this thing with you. All notes are available. Suppose we are taking brain tumor image. For example, you are working on classification and you have taken a research topic, quantum machine learning for brain tumor classification. That is your research work. Now, size of an image of a MRI is 24, 20, 224, 224, and also it is let's say RGB color format. This is MRI, but MRI is grayscale. You take not MRI. Okay, take color images there. Color images there. So it is 224, 2243. This much number of values will be there, or even larger. If it is grayscale, then it is 224, 224, 1. All right, you can do the multiplication, how much it comes. Let's say any of the number near to this. So 2 to the power n, 150, 528. N equal to 18. That means number of qubits which are required for this is 18. So qubits just to load one image and preparing such states itself is difficult. It will take I don't know how many days to solve a problem on your local machine. In fact, you will say, sir, we will use machine learning or deep learning or convolution, any other we will use, we will not use this quantum. Quantum with a name told, sir, it will solve complex problem, but it will itself stuck in such kind of scenario. Simulating 18 qubits with deep variational circuit on classical hardware, very expensive. It will solve in one day also, I'm not sure. Anyways, the pipeline would be like you will apply MRI image, color image, not MRI, color image to convolution neural network, extract the features. Then apply PCA, further extract the feature, demonstrate. Then from there, just try to get only 4 to 12 features, and then apply the quantum circuit, and then perform the classification. Well, this will be the research idea. This will be the flow. I can't do anything else. If you expect 18, no. I can take 2 or 4 qubits, enough, not more than that. I don't have any machine to solve the problem. Got it. In regards to this, here is the project which I am supposed to do. I've already shared with everyone. Again, I am sharing. You need to run this with me side by side. This is potato classification, potato disease classification. Please check the comment. I've shared the code with you. Okay. Potato disease classification. Let's see what we are doing in this case. Potato disease classification. The data set, if you ask how it is, let me show you the data set also. Here is the data set. Potato disease detection data set. Okay, here it is. Potato disease detection data set. It is having three categories: potato early blight, potato late blight, potato healthy. Blight means affected by early blight caused by some fungus. Late blight means a serious disease caused by some infestance, might be some infection, fungus, bacteria, or whatever happened. Healthy will all no disease symptom. So three classes are there. Okay, and this project is related to plant pathology and agriculture. We do have the journals where they publish papers on agriculture and plant diseases. Okay, this project will be beneficial, which includes quantum also, deep learning also, and plant disease detection also. Okay, now you can see the images. Uh, Here are the images. Okay, any of the category I can pick up. This is potato early blight. Okay, or potato late blight. You can see, and potato healthy. Here the leaves will be green. You can see the leaves are green. They are healthy, no? They don't have any fading over the leaves. If they are affected by fungus or bacteria or etc., the color will change. You can see the color. Here color is changed, yellow, pale yellow, and some brown spots are there. So these are infected leaves. Okay, with the help of these we can identify. One more thing I just want to clarify here. Every study is a detailed approach. Since we are talking about zero, one, zero, and one both. We're talking about this. Okay. We are expected to create quantum circuits where zero can be given as an input, one can be given as an input, zero, one both can be given as an input, one, zero can be given as an input, zero, zero can be given as an input, one can be given as an input. Why? Because it supports a superposition, superimposition. It supports that. Okay, such kind of circuits we are creating. They will be passing through unitary function, and this unitary function can take one qubit, two qubit, three qubit, multi qubit. Depends. The function will also change. That's also you have studied. Rotatory, Hadamard, identity, rotation, X, Y, Z, all these things you have studied. So these functions are applied over digits, and they change the orientation of the digits. And this orientation will be followed like having superimposition or multiple states. Then you have seen the circuits. Here are the circuits. There's a connection like this. These are called as quantum circuits. Later on, we can have certain layers. We can have certain layers. Depends how much kind of like architecture, depth architecture you are building. So we can have a layers. Can we use it as a plant bioinformatics? Yes, we can, madam. Yes, we can. Okay, this is Muhammad Nadeem. Okay, from Pakistan. Yes, not madam. Sorry. Yes, Nadeem, we can take it. Okay, depend upon the layer. Again, I can extend the circuit. So layer one, layer two, we can have three layers also. Multiple layers can be there. Then later on, you can have your machine learning concept. So till like we can create a quantum, and and these bits are operated by rotation, Hadamard, identity, etc., kind of matrices, metrics. They are quantum unitary functions, converting these bits into quantum format. Then circuit will solve it, give the result. Again, maths. These what these matrices are maths only. Okay. Ma- Without maths, nothing is possible. And metrics, representation of bits. If I talk about the data which we are taking right now, potato or any other kind of data, it is very much important in agriculture field under what condition data is collected. Very, very much important. You are having bright images, you are having dark images, you may have corrupt images. It is very much important in what scenario data set is collected. Why model fail? Why machine learning model fails? In case, for example, you have trained your machine learning model over this particular data, potato data, and the potato images are taken in a very good environment. There was so much light present. Okay, and your camera quality was very good. This is how the images are collected. But when you put it into the real world, it may happen that such a scenario, such background, such environment may not be present. So your model may be failed to recognize this particular image. It happens. Anyways, we while training a model, we do augmentations, several types of augmentations. Okay, fine. Like we rotate the image, we flip the image, we increase the brightness or decrease the contrast, and we zoom the image, flip the image, or do a lot of things. Augmentations, resize the image, many things, many transformations we do, just to make a model understand that if the complexity is present in the data, still you need to recognize that this is healthy, this is a diseased kind of image to classify. Why this? That's the reason we do the augmentations. But still, it's challenging. Still challenging. You are working on 2D images. Also, only image will not give you the entire idea. That is why right now many people are working on multimodal models, which have text also, image also. I want some explanation related to the images. And 3D, not 2D, 3D. I need more details to conclude. Simple 2D image classification is now over unless and until you come with a solid idea. They're multimodal or 3D images. Classification, segmentation. Anyways, so I do have this potato image, and we want to work using quantum machine learning over it. Well, here is the flow of the project. And over the Kaggle, okay, you can do one thing. You can go here and you can copy and edit my notebook easily. Just copy and edit my notebook. You and run all. You will get all the results. Fine. I imported the basic libraries, NumPy, Pandas. Here is the base path of potato disease detection. I am having three categories available with me, and I have created a data frame. That is the easiest way to represent the data according to my understanding. Okay, so image path and the label, where the image is present and what label it do have. healthy or diseased or whatsoever. Okay. DF dot head, 5 rows, first 5 rows, DF tail, last 5 rows. I don't have that much images. Okay. Only 2151 images are there in total, including all the categories. Only 2151 images are there. DF shape, DF columns, no duplicate, no null value. Okay, unique labels are potato early blight, potato late blight, potato healthy. These are the categories. Value counts are like this: 1,000 images for early blight, 1,000 images for late blight, and 150 images for healthy. So it's an imbalanced data. Okay, healthy images are less. We'll need to balance it. We'll see. Here is a distribution: count plot and pie plot. Okay, 1,000 each, 152. Here is the pie chart. Okay, fine. And then 5 images from each category I have displayed. Here you can see early blight, late blight, healthy. 5 images from each category I have displayed. Here is very basic code. Just read the image, convert the color it into RGB, and prepare a subplot for each category. So it's not any hard and fast code I'm doing in Python. It's very easy code. Got it. And then next, what I have performed, just ignore warnings. Okay, any warning come na, then ignore it. That the library I have taken. Penny Lane, yesterday also I have used in my notebook. Today also I am using it here, Penny Lane. So pip install Penny Lane. If you want to use first, you need the installation. Okay, so Penny Lane is installed here. After the installation of Penny Lane, I have imported the libraries, required libraries like Torch. Torch, like it's a deep learning framework. Okay, Torch or TensorFlow, whatever you like, you can. Torch is, I am recommending from my side. So Torch, neural network, Torch optimizer, load the data using the Torch, and then transformations and models. Okay, so Torch taken here. Then some basic libraries, Matplotlib, Seaborn already done. Sklearn classification report, confusion matrix, because this will be a classification problem. All right. To show the training progress, I am taking TQDM, training progress. Uh, Three unique labels are there. Let them name as 0, 1, and 2. Give ID to them: 0, 1, and 2, enumerations. Okay. Then do one thing: split the data into training and the testing. Okay, do the splitting and only balance the training data. Don't balance the. Okay, I think I've cleared many times in my workshops. Here also I'm telling that don't balance the data first and then split. Don't do that. First split and balance only training. Don't touch testing. Only you have to balance the training data. All right. So first split your imbalanced data. Whatever my data frame is, I have splitted. Then I find what's the maximum number of samples in the training, what's the number, and then I am balancing by just sampling the data, random sampling I'm doing. So whatever be the minority class, that will become equal to the majority class by just doing replacements, duplication that will happen, and the number gets increased. It's a random sampling. All right, and balanced data frame is created. So remember this thing. If you don't do, there will be data leakage, and at the end, your model will become overfitted. Remember. All right. So this is brain tumor written, but it should not have to be a brain tumor. Um, because I've done the code for brain tumor, my flow will remains the same. So it may happen that the name will also get copied. Okay, so it's not brain tumor. You can change this to plant data set or potato data set. Okay, you can change the name. But anyways, Machine doesn't understand whether you are working on a brain, whether you are working on potato. Okay, machine, if the code syntax is proper, proceed. Anyways, so here what I'm trying to do is I'm going to apply various transformations over the image, and these transformations are resize the image to 224, perform horizontal flip, give a 15-degree rotation, kindly make the brightness by point to change the contrast by point to convert it into tensor, and then normalize every image between 0 to 1 pixel values are there. So some kind of transformations I have applied here, that called as resizing. Horizontal flip, I can add vertical flip also. Rotation by 15-degree, I can do 5-degree or 10-degree. Okay, and then increasing the brightness and the contrast by 2.2, this much percentage, and then normalizing the pixels. This I'm doing on training data. And why I'm doing all this on the training data? Because we never feed directly available data to the model for training. No, we want model to learn complex patterns in the data. And how the complexity will come? The complexity will only come when you do the augmentation over the data. So this is the augmentation or transformation which I have done. Anyways, then over validation data also you can do some augmentations like resize, and normalize the pixels. That's it. In validation, not required that you need to horizontal flip, vertical flip, and this, no, not required. Only during training we want to make the things complicated. During validation or testing, no complications required. Just keep it as it is. All right, fine. So I have prepared my data. Okay, and what I'm going to do here is I will be using ResNet 18 model to extract a feature from the images. That's what I'm doing. So first will be feature extraction. You can change the model from your side. Currently, I'm using ResNet 18 pre-trained model for feature extraction. Okay, I guess you guys have worked on pre-trained models for feature extraction in images. VGG 16, 19, Inception, Exception, ResNet 18, ResNet 50, ResNet 101, ResNet 151, or 152. Long range models are there. All right, so feature extraction. After doing the feature extraction, okay, after doing the feature extraction, I'm applying PCA and scaling the data. Already such kind of flow I have made in my document. I already explained to you. This flow I have already made. And if you want me to explain these steps also, I made some notes for you. Okay, like here it is. PCA, you very well know, principal component analysis. For high variance, I'm expecting so that I can get good features. Standard scaler, obviously, we need to scale the data. All right, and here number of qubits I am taking 4. Okay, that's also mentioned here. Number of qubits 4. Intermediate dimension I'm taking 32. That means 32 is likely the size of the hidden layer in a classical model. That is a machine learning model. 32 is the number of neurons present in it. When we are going to create a hybrid model. Huh? So a number of qubits, that is for quantum. An intermediate dimension, that means when you are going to make a neural network for classification, there you can take 32 neurons. Okay, that will be intermediate dimension. Okay, so 32 will be as an input. But we'll see. First of all, what's happening? In the above case, I've used ResNet to extract the features. These features will be given to the PCA. Okay, first scale those features, then give it to the PCA, component analysis, and expect 95% of the variance to be recovered. Whatever be the components we are getting, we are expecting 95% of the variance should be there. If the variance will be less, if the information will be less, then you are applying quantum circuit. Model will not learn. Remember one thing, it will not learn. With 20-30% variance you will fail. I am expecting at least 95% of the variance to be retained. All right, therefore our process here, it's very simple. You will give all the images to the ResNet 18. ResNet 18 will extract the features and keep it. Extract features and keep it. Then these extracted features will be passed to standard scaler for scaling. Formula for standard scaler is x minus nu upon sigma. So it will scale the features, make them all in a perfect scale or distribution. Then we will apply PCA, principal component analysis, to align the components and capture maximum information. All right, and I'm here expecting that whatever be the number of components you make, I want 95% of the information to be retained. That's what my expectation is from the PCA. All right, so here I'm doing that. Apply to the PCA, and you can see 95% variance ratio. PCA components are 220 kept. It came as 220. So 220 components are created, and 95% of the variance is explained. So this is the PCA shape. As you already know that I cannot work on entire data set. Whatever be the features extracted from the model ResNet. How many features are there? 512. This much features are there. 2400 is the number of rows. ResNet captured 512. Okay, so 512 not possible. Okay, that is why I applied a PCA. And this much components kept. And then what I did? Next, I am creating a quantum circuit. This is quantum circuit. And what I am taking in the quantum circuit, first of all, create a quantum device. Number of qubits, number of wires, n qubits. The number of qubits are 4. I am taking 4 qubits, 4 wires, 4 as an input. Then here I am creating the entire circuit. In the entire circuit, I am taking angle embedding, basic entanglement, okay, and taking poly. Why I am taking these? What's the reason? How many number of qubits are there? This is multi-qubit. Okay, this is multi-qubit, not single qubit, not two qubit, not three qubit, multi-qubit. Now, if we check again the quantum gates, multi-qubit, multi-qubit, or here we can use complex logical operations in multi-qubits. But let's say we are having four at the moment. So with the four, we are applying angle embedding, basic entanglement, and poly Z. Check what they are performing. According to poly Z, it will change the phase of the qubit using phase encoding and quantum error correction. One thing is this. Then, what's more here? Angle embedding. Okay, so we will be using rotation for angle embedding. Rotation feature encoding for X, quantum neural network for Y, phase encoding for Z. C naught will create entanglement. We want angle encoding. An angle encoding is let me again let you know because we have seen that angle encoding part. Okay, flip the target, Z, Y condition. Okay, CC naught. I've also seen that angle encoding one. Mhm. Here, change the phase. Okay, here phase encoding. Rather, I can call phase or angle. It's quite similar. Okay, that is why we are applying poly Z. Okay, so here 90-degree phase shift, 45-degree phase shift. Okay, phase encoding. So I just call it phase or angle. That will be nearly same only. I am just specifically using for that looking for that word phase. Phase or angle will be like same only. You can search on option to find. Yeah, madam, but like I understood that phase has been written. So phase is angle only. Okay, because 45-degree phase shift. Phase is angle only. All right. So here the circuit has been prepared in our code. Angle embedding, basic containment, and I'm taking rotation y. Rotation y, what it means? Rotation y is widely used in quantum neural network. Okay, so we are preparing that. Then basic containment layer to find the relationship or means connection or influence between the points between these circuits. And then we are using poly z. We are taking poly z here. Poly z change the phase of a qubit used in phase encoding and quantum error correction. All right, in a very easy way, this quantum circuit has been prepared. Angle embedding, rotation y is used, r y theta is used. Entertainment to have an interconnection between these quantum bits we are using, and poly has been using in order to find the error between them. That's what we are using: phase encoding and also quantum error correction. That is why we are using poly z. Total three layers of this circuit will be prepared. So one angle embedding, basic entailment, poly. Again angle embedding, basic entailment, poly. Again angle embedding, basic entailment, and the poly. So like in this way, three layers will be created. Parameters are defined like weights, etc., etc. Last day also we have seen the parameter definition. Here also parameters are defined. Weight and the bias are the parameters. Then what I'm going to do is, here the hybrid model is considered. Just take a sequential model. Take linear layer, normalization, ReLU, dropout, linear, tan activation function. Okay. Then Q layer, in which again sequential linear is used. Fine. Then okay, Q layer. Okay, I'm going to attach Q layer here at the last of the my classical, or let's say deep learning neural network. All right, the forward pass will take like this. X will be given to classical pre. So this is classical pre. That means you will give the input to these layers. It will pass through uh, 32 will be the input dimension. So input, that will be 32 features will be given as an input. There are 64 neurons present in linear layer. Then there is a batch normalization layer. Then there is a ReLU layer, then dropout layer, then again linear layer. And it will give me the output 4 qubits, because now this will be given as an input to the quantum circuit. Okay. This will be given as an input to the quantum circuit. After quantum circuit, again we are taking the output from the quantum circuit and passing it to the linear layer to get the final classification. Okay, so that's why it's called as a hybrid layer or a hybrid architecture. So first is your classical, then your quantum, and then at the end again classical. To do the classification, there are three classes present in it. So we have merged quantum circuit in between, deep learning layers. That is what we have done. This is hybrid in nature. Got it. I do have a data, and I will pass the data. 30 epochs it will take to perform the iteration, and after 30 epochs, I am getting accuracy is 99%, 99.79% accuracy. While evaluating this model, here is what you can see: 99% accuracy we are getting for a classification. And what I have used? I've used ResNet 18 for feature extraction. I applied PCA to reduce the dimension. And after PCA, I've created a quantum circuit separately. and then I have created a hybrid architecture. In the hybrid architecture, because already ResNet has been applied, now there is no sense. Please don't incorporate any other pre-trained model again here in the architecture. No need, na. We already extracted the feature from the pre-trained model. Why to use any other kind of pre-train? Here, don't use any kind of pre-train. Oh, only linear layer, only neural network. Okay, nothing else. So linear layer is a dense layer. It's a hidden layer. So here input dimension is 32. Well, what we are doing, let me create the entire scene in front of you. The entire scene is like this. Images to ResNet 18 to PCA, and after PCA, now you are going to give this into a hybrid model. Hybrid model. In hybrid model, you are having neural network first. Linear layer, the number of input will be 32. Then there is 64 neurons, linear layer or hidden layer. Then there is batch normalization, ReLU, then again linear layer will be there, something like this. Then after that, the output will be having 4 qubits, 4 bits will be there. These 4 bits will be passed through quantum circuit. In quantum circuit, we are having one phase embedding, we are having entailment, we are having poly Z. Again, I am adding after whatever with the output I am getting, I'm adding it to one linear layer in which, let's say, 3 neurons are present. This will give me the final classification. That's it. This is hybrid model, entire hybrid architecture for potato disease classification. Here is your quantum working. All right, fine. So therefore, you can see the results what I got, and it will not take much time for training. 99% achieved. Here's the confusion matrix classification report. This is classification report. Here's the confusion matrix. Quantum hybrid model. Alright. So you prepared a quantum hybrid model. Now, sir, how we can also practice from our side? It will take time. It will obviously take time to prepare such, especially related to quantum. I know you are well aware with the rest of the models. You can easily make a ResNet and a DenseNet and efficient net. You can add linear layer neural network. And the work is already over. We don't have much out of it. If you want something different, then quantum is here. Okay. The only thing which you need to learn is to how to prepare a quantum circuit. All right, and that will be done only when you read in depth related to what quantum gates are doing, because your entire work is based upon quantum gate only. Okay, when to use rotation X, when to use rotation Y, when to use rotation Z, when to use poly X, poly Y, poly Z, when to use Hadamard, when to use C naught, when to use CC naught, when to use any other kind of gate. You should be aware of that. Now, if it is your research area, then obviously you need to do. If it's not your research area, then it's new thing for you to learn. Depend upon your practice, you can perform, and you can publish your articles also. That's what you can do. I use logistic regression also. With logistic regression, I again got 99% accuracy. But if I compare these two, logistic and quantum-based hybrid model, the logistic is 98.84, round off is 99, and quantum is 99.07. So, if you compare and put somewhere in the research paper, research article, so they will tell that in logistic only you got 98.84. Why you created this much? You yourself put in trouble, and other people also in trouble. Only for how much? 0.06. This is 98.84. This is 99.07. Okay, so how much difference you have achieved by this? All right. Anyways, but we need to do with it. So here are the final answer accuracy comparison. I have used logistic regression. You want, you can use any other machine learning classifier to perform. can use support vector classifier, random forest classifier, decision tree classifier. Use all the models here and compare with your quantum, how much results you are getting. And what kind of comparison? Already 99% here. There's nothing left. Anyways, I have done this project in different way also. One more code. Now library will be changed. I am using Penny Lane, but here I am not using Penny Lane. And this code I have done with respect to a research paper. Here is a research paper. Quantum machine learning for image classification, a hybrid model of residual network with quantum support vector machine, published in next generation computing IoT and machine learning NCIM 2025. Might be some conference or whatever. Here this paper is published. All right. Now, what they have mentioned, let's study from the abstract. Recently, there has been growing attention on combining quantum machine learning with classical deep learning approaches as computational technique as key of improving the performance of image classification task. Boss, image classification task is already improved. Now, many of the people are claiming we got 98 and 99% accuracy. Anyways, we need to do something else. So this study present a hybrid approach using ResNet 50. Okay, okay. So what we'll do? We are already having potato data. I have used ResNet 18. Replace ResNet 18 with ResNet 50. Only one change. ResNet 18 with ResNet 50. Extract the feature. For feature extraction and quantum support vector machine for classification in a context of potato disease detection. Classical machine learning as well as deep learning models struggle with high dimensional and complex data set necessitating advanced techniques like quantum to improve classification accuracy. What they are saying, classification has been affected by high dimensional data. Obviously, we don't take high dimensional data. Okay, we do feature extraction and feature get less obviously by feature extraction, and by creating neural network we further reduce the features. We only take relevant features by creating such architecture. Here they are saying high dimensional they struggle, therefore use quantum. Obviously quantum cannot work on high dimensional data. In our research, we use ResNet 50 to extract the D feature and RGB images of potato. These features are subject to density reduction (PCA). So we already did, yeah. Already we applied PCU in ResNet 18. Then we applied PCA. So you are saying that do the same thing and apply various quantum maps such as Z poly X to transform the classical data into quantum state. Okay, we have also done the same thing with Penny Lane. Same thing we did. We applied rotation, phase encoding. We apply entailment, connection, influence of one by another, and we also applied poly Z we applied. You are talking about poly X. They are talking about Z and Z. Okay, let's check Z. What is this Z? Okay, check whether it's mentioned here or not. I think I have seen somewhere Z. Okay, CZRXRY. Okay, I've seen somewhere. Here it is. Multi controlled Z. Generalized control Z gate. That is Z. Okay. What else? Yes, one I got. This is CZ. Apply Z gate if control qubit is 1. Anything else? Mm, no. Here are the matrices of swap, C naught, phase encoding, all these are the matrices. Okay. Now the question is, sir, when to apply when? Now you will ask, sir, whether we can apply sir rotation X or we can apply rotation Y or whether we can apply rotation Z. What we can apply, sir? Well, according to me, I understood that depend upon the number of qubits we need to prepare our architecture. If the qubits are, if you're taking single qubit or double qubit or three qubit or multi qubit, according to that you need to identify the gate. that you need to learn. Here the application is present. Okay, for single qubit, for double qubit, for triple qubit, for multi qubit. Accordingly, you prepare the gate or take the gate. Okay, and as per research paper mentioned that they took Z Z Z and poly X, take it. And after doing this ZZZ poly X, they assess the model performance in comparison to support vector machine and SVM and random forest with the hyperparameter tuning, five-fold stratified cross validation. QSM got a 93.23% accuracy. Okay. Logistic regression got a 98% accuracy. Already we have seen. This is the abstract. That's it. Now tell me. This is the abstract. And I have already shown you, demonstrated a code in front of you. You have seen that particular code. Few changes we need to do in our code, and that will be done. However, in this new code, I'm not using penny lane. In this new code, there's one more library called as qubits. Okay, qk bits like that. Let me show you the library. Initial code is entirely same. Okay, no need to worry. Entire code is copy pasted. Only here this is the change. First of all, instead of ResNet 18, I took ResNet 50. Only one line change as taking a reference to the research paper. Okay, in this code, we are having ResNet 18. Okay, I copied the entire code and instead of 18, I changed it to 50 because I saw the research paper. Okay, got it. So, here, here, ResNet 18, pre-trained true. Got it. Then okay, same code. Then PCA, same code, same code. I took PCA number of components 9 here. What I can do is I can change it as I did here, like this 0.95. Here I mentioned, but here I took 9 components. I think 0.959 will be not that much different. But here what happened? The variance explained came to be 44%. Okay, 44%. And with 0.95, it is coming to be 94%. You can see 95% like variance ratio is 0.95%. Okay, so you do one thing, copy paste this entire code, okay, and paste it here, okay. Or you do alternative, instead of 9, na, you change it to 0.95. That will be fine. Okay, there are certain libraries which I need to install apart from Penny These are QISKIT, Qubits ka QSkit, QSkit machine learning. However, I found Penny very easy, but in the research paper they mentioned QSkit libraries. All right, so that is why I need to install these libraries. Pip install QSkit library. Here also all the installations done. And here I am taking ZZ feature map, and poly feature map. There I haven't taken any feature map. Here I need to take the feature map because of this library. If I would have used Penny Lane, then not required. But it's required here. From the circuit, we need to pick up ZZ, Z, and poly. Okay. I've also made an explanation for you. Here it is, an explanation. Here is the explanation for these libraries. Okay, QSkit is an open source quantum computing library developed by IBM. हाँ sir, IBM का तो quantum है. Quantum is means if I hear the name quantum, then it comes IBM automatically will come International Business Machine. So these people have developed this library, then we need to give respect. So it's an open source library for quantum computing framework. Okay, and like from here we can create the quantum circuits. These are some code like how to build a quantum circuit using gates such as okay Hadamard. We already seen. We have already seen. All right. So QSKIT can connect to the IBM quantum processor and execute circuit. We don't have any quantum processor. We don't have any quantum hardware. Unnecessary or like as per research paper. Let's take it. Let's take it. All right. Yeah, at least you should know that what are the possible options with quantum. But I struggled with this QSKIT. With Penny Lane, not, but QSKIT because they are specially designed for quantum. They are specially designed for quantum framework, quantum hardware, quantum circuit. Penny Lane also, but it gives simulation. Here, for some code running, it took time for me. Anyways, so all these details you can read from your side. It's mentioned here. Okay, got it. All the details you can read. Okay, then I do have quantum kernel and quantum support vector machine. So quantum do have their own algorithms, just like traditional machine learning algorithm. Quantum support vector classifier. Support vector classifier we already know. They do have quantum support vector classifier. And what happens in support vector classifier? We create a decision boundary in support vector classifier. We create a decision boundary between class A and class B. There is a hyperplane which classify A from B. That is what we make support vector machine. Okay, but a algorithm specifically designed for quantum, then we call it as quantum support vector classifier. We are importing it from QISKIT. So first install, then import feature extraction technique and the classifier model. Okay, got it. Actually, I faced some issues while installation. One library was not getting installed, so again I uh, like installed them. Reinstallation happened because there was some issue. One library was failing. There was an error coming. Okay. Anyways, I did that. Then I gave the features extracted from ResNet 50 to Z feature to ZZ feature to poly feature. I performed the feature extraction from them. Okay, and these features are projected over kernel, Z kernel, ZZ kernel, and PX kernel. Why kernel? Because support vector machine has a kernel. Okay, it do have a kernel where we project the data points. So, and there are different kinds of kernel in SVC, support vector classifier. If you pick up traditional machine learning algorithm, and these kernels are linear kernel, RBF kernel, sigmoid kernel. There are different kinds of kernels are present. All right. So what I'm doing here is created the feature maps. Okay, created the feature maps. Take how many qubits are required and define the kernels. So all the kernels will be ready to perform the classification. So feature map and the kernels. Okay, these are traditional machine learning algorithms. Support vector machine and random forest. This is for cross validation. Cross validation. The accuracy coming to be 94 for SVM and random forest 93. This much accuracy it's coming. Anyways, I took quantum XQ SVM, YQ SVM, all these I have taken, all these features I have taken. From where I have calculated these things, XQ and YQ SVM, check here. Uh, I have identified them. PCA we have performed. PCA we have performed. These are identified from all the X values, all the Y values from here. After doing shuffling of the data. From there, I am only taking 30 values and 10 values. Okay, only 30 and 10 values I am taking. And what kind of architecture I have prepared here? I have prepared an architecture which which is having feature extraction, PCA, and quantum SVC. Only these things. This is the architecture, simplest architecture. Presence of Z features, poly features, and kernels. These kernels are defined for support vector classifier, quantum support vector classifier. These are traditional machine learning algorithms, leave them because here the kernel is ready for quantum support vector machine. Then apply apply the data, apply the features to quantum. QSVC, Z kernel, QSVC, ZZ kernel, QSVC, PX kernel, poly kernel. So I am applying my data, training data, to these three different kernels: Z kernel, ZZ kernel, and the poly kernel. This is called as training of a quantum support vector classifier. I'm taking very less data. First of all, I took 1,000 number of data points, but the code is under execution and under execution. Then I stopped. Then I took 300 features, 300 rows, 9 features only. This data again it was under execution. Then I changed it to only 30. 30. I am taking only 30 images. I am taking from the training data to train. Already, support vector machine is a hectic classifier. It's one of the complex maths support vector machine in entire ML. So taking quantum SVM, it will take a long time. It took long time. So with 30 images I am working here. Training also and testing I am taking only 10 images. This much I am taking. Okay, got it. Only this one. And then I'm using all these three kernels Z, ZZ, and poly. Training over these images, doing the predictions. I got accuracy 70%, 10%, and 80%. And then I'm printing the classification report. With quantum Z, best 70, like best with quantum Z feature map. 70% I'm getting. I think with poly also I got 80%. I could have printed for poly also. This one failed. Quantum ZZ. It's only 0.1, 10% accuracy. With quantum Z feature map, I'm getting this much accuracy, 70%. So what I did, let me again explain you. Very easy. As I made this architecture, now I will make this architecture also. You are having images. You pass the images to ResNet 50 for feature extraction. Once you got the feature extraction, you have passed to the PCA, principal component analysis, to achieve the high variance. And fortunately, you got 44% or something kind of variance available with it. Previously, with 0.95, you got 95% of the variance retained. Anyways, after PCA, you need to pass it to quantum support vector machine. You need to pass it here, QSVM. All right, in QSVM, what you have? You are having Z feature, you are having ZZ feature, you are having poly feature. All right, so pass all of them to these features, then kernel, again Z kernel, ZZ kernel, and poly kernel for classification. This is for classification. These kernels for class. That's it. You got the result. You got the result. बस यही है. This much done. And we are having separate kernels. Like these three are the separate kernels. You applied. You got the scores for Z. You got 70%. For this, you got 10%. For this, you got 80%. I displayed the confusion matrix and the classification. That's it. This is the architecture of the research paper using QI skit library. Okay, Penny Lane was better, where we make the architecture in different way. Here we are not using neural network. We are using QSVM. There we have used neural network. Remember, our previous architecture was with Penny Lane is amazing. This I made just to refer to the research paper. That's it. And this is like the steps mentioned in the research paper. QSVM, quantum support vector machine, with three components Z, ZZ, and poly. Okay, Z feature, ZZ feature, and poly feature. We have extracted from the images, and I took only 30. I got stuck. Code, I don't know how much time it will take to run. And computational complexity is also one of the things. You're running on CPU, applying quantum, using QI library, not preferred. Anyways, I hope this makes sense. Here is a research paper and demonstration of the research paper. 6-page research paper is this. Okay. So, like the data set, pre-processing of the images, ResNet feature extraction, then QSVM they have given. In QSVM, we are having the feature map. The feature map will be passed to whom? Unitary circuit, unitary component. In Pennylen also we were doing the same thing. Here we are having ZZ, and poly. There we were having face embedding. We were having entailment and poly. Giving it to the kernel. Kernel is for classification. That means projecting these features over the kernel, because obviously we need to do support vector machine works on kernel only. Okay. Later on, they will be converted into measurements, and here are the result healthy and all. This is the architecture. ResNet inspired quantum support vector machine classifier model, disease classification. Okay, here are the results mentioned. The random forest gave 96%, and SVM got 99.23%. They are not mentioning how much time it took on the machine. And if you are doing a simple classification on a quantum machine, then why you are purchase this much big machine? How much cost it will take to purchase a quantum machine? For what reason you have done the quantum? This task 99 I can achieve on Torch and TensorFlow only. Machine learning itself algorithm. See, machine learning algorithm giving 96% accuracy. You are giving 99, and 99% accuracy is again it's not justifiable. Anyways, it happened. We did. I need to explain you the concept. We did. That's it. So if you are working on quantum, be cautious. Okay, and things will go in like what kind of circuit you need to, what kind of gate you need to take. Check the gates. Okay, both the codes I got poly. I think poly is common. Now phase encoding or anything else you need to take, just check it out. Change the architecture. Publish the paper. Okay, that's what I need to teach in the session. Yes, anything you want to say? Any doubt? Anything you want to share? Let me know. You want to say something, please? So remember, in 2 days, what we have learned, creating quantum circuit require quantum gate. It will take qubits as an input. You should have good knowledge about unitary circuit, that this quantum circuit, these gates. That's it. You should know how many qubits are required for having this unitary circuit. Okay, I have given you two codes. If we have to increase the accuracy, we need to use Penny. No, madam. Actually, Penny Lane is easy library to work upon. For increasing the accuracy, no, madam, you require a good amount of features to be present. But we are in a like say deadlock. If we keep so many features, the circuit will be increased and it will take a lot of time for execution. That's why I'm reminding again and again. I don't mind that you want to increase the accuracy. For increasing accuracy, features should be more to consider. But It will complex your circuit. So we need to keep less features if you are working on quantum or over CPU because we don't have quantum machine. Okay, for increasing the accuracy, features variance explained should be high. Then quantum will give you good result. If the variance explained is less, features less, getting high accuracy is challenging here in quantum. Okay, please take care of that. Got it. So like our architecture, deep learning also you have seen, quantum support vector machine also you have seen. And what's the change? What kind of paper you will see in in publication? Such kind of paper only. So far, no. Like who is going to purchase quantum machine to do classification? Do you think that to achieve 99% accuracy, you are going to purchase quantum machine? You can get with by deep learning models only. But but if it's a different perspective for you, then try. Okay, different perspective, then try. Okay, like okay, here it is. Anything which I can show you for attendance? I can take the attendance. I guess it's clear for everyone. Yeah. Any other doubt? Please let me know. Can we use the model for other application? Yes, sir. Obviously, brain tumor also possible. Same code, no change. Same code. Just change the data set. That's it. Same code. Just change the data set. Yes, Lalita ma'am. Please say.
Yes, sir. So today just read one blog related to the same potato disease
Hmm.
classification,
Hmm.
and in that they mentioned that the two level that the model. In
Hmm.
the first level, they used a yellow model for the leaf segmentation, and then it is a real time application
Hmm.
is there in that block, and then this is classification using the simple CNN model.
Hmm.
They got the 99.75% accuracy.
Hmm.
So in that case, when we use this QML model and this hybrid approaches, we got below that accuracies.
Hmm.
So how my question is that how we defend with that the accuracy, because they already reached a
Ah,
99.75% accuracy, and by using our model we got a 99.28 something accuracy.
Madam,
So
as per your question, now accuracy is right now not a concern. I already explained in the like previously only, most of the models with TensorFlow or Torch, we are taking pre-trained models. They have achieved 99% accuracy. In fact, the machine learning model, I think I have shown. Okay, this machine learning model got 98% accuracy. So, madam, what is the difference between 98 and 99? Simple machine learning logistic regression model getting 98% accuracy. So, here research is not at all related to getting accuracy. All right, madam. So, if you compare, they got 99.75, they are already the winner. Okay. Now, for what purpose quantum we are using? You need to defend in a way that in this data, such and such complexity is present, which is difficult for other models to get. So, what kind of complexity is present in this plant disease data set? You need to defend, which can be solved by quantum circuit. So far, I haven't identified. Let me tell you clear, because other models, they are good architectures. The results are also fine. Okay, but if you are researching, then you need to identify that what problem is in the data set. You require quantum. What complex features were present which other can't identify? You have identified. What's the reason? And if you talk about novelty in quantum, what kind of novelty you want to put in the quantum? You are already available with the gates, Z gate, for this gate, rotate, all the gates are there. Just you need to organize and apply other algorithm. Feature extraction will be done by ResNet or DenseNet or any other algorithm. Instead of ResNet, use DenseNet. Well, if you want to do some changes, change the model. Change the feature extraction model. Okay, so I think so. Since the models are designed for image classification, it can potentially be adapted for other medical imaging. Yes, they can be done. They can be done. Quantum is designed for superimposition of the bits for complexity. Okay, because that multiple bits use case is for complexity. You need to defend what kind of complexity is present in the data set, which is not identified by others, and your model is identified. If you can tell, then that's a justification. If you cannot tell, then it's not been justification. It's just a simple, you applied quantum and getting accuracy. And we can
Okay,
apply this entire code, just copy paste and use change the data set. Change the data set. Take brain tumor, work, it will work. Okay, but the point is quantum is used for a purpose that energy levels and this and that justify that what kind of complexity you faced. As madam has already told that, sir, I have seen some article which got 99.75. Now we are not expecting 101 accuracy, 101% accuracy. That is not possible. In fact, if I get some paper 99.75 also, I will not show. I'll write that 99.75. It's not possible. This is not a generalized model. This is an overfitted model. My model is generalized model because it is solving these problems. Then we'll
okay,
see how the editor will think of the general. Okay, fine. So I guess in these 2 days. Oh, okay. I also saw one poster of quantum machine learning, and there was one professor, I don't know who was outside. uh, okay, he was charging 600 US dollars. I thought that I did a mistake. Then he is charging 600 US dollar for a course on quantum machine learning. You know how much? $600. Sir, please, this paper, which is I will share this paper. All right.
so again that this is a